Where's my camera? I should be showing up here in a second. There I am. Okay, let's get into it. Howdy, everybody. I hope you're having an absolutely lovely day. I know I am, and it's only going to get better in a few minutes here. My name is Tim Sylvia. I'm an editor with PV Magazine USA, and I'll be your moderator for today's webinar, Understanding and Mitigating the Dangers Posed by Hail and Wind. Joining me today are two excellent presenters, Sharif Kadir, CEO and President of Renewable Energy Test Center, and Kent Whitfield, Vice President of Quality at Nextracker. Before we hop into the webinar, we have a little bit of housekeeping to take care of, not too much. This webinar will consist of a brief presentation with audience Q&A at the end, though you're free to submit questions at any time during the presentation. Due to time constraints, we may not have time to address every single question, but we'll certainly attempt to, and we can redirect any super pressing questions to our presenters at a later time. If you've ever attended a PV Magazine webinar before, you may notice that this platform looks a little bit different this time around. Webinar will still function in the same way that others have, just with a different interface that allows for better interaction with you, the audience. If you have any technical difficulties during the presentation, just try refreshing your webpage, and if problems persist, shoot us a message and we'll work to resolve it. In addition to myself, my colleague Beatriz is waiting in the wings to assist with any difficulties. Okay, now that the housekeeping's all taken care of, let's switch our focus back to the topic at hand, large-scale solar's interesting and not always friendly relationship, in fact, frequently unfriendly relationship with hail. As the market for utility-scale solar installations expands geographically, these projects are going to be faced with a wide array of extreme weather and have to be prepared to withstand the elements. Wind and hail pose significant threats to solar installations, especially as large format modules proliferate into usage. Mitigating the threats posed by these phenomena is an uphill battle against physics, costs, and even current industry testing standards and resilience standards. Hail damage may represent approximately 60% of PV system financial claims, while still being relatively infrequent at 3% of insurance claims. These high-impact, infrequent events can even be difficult to assess for and plan for mitigation. Mitigation, that's one word. To better understand why hail can be so destructive, why the reality of the situation may be less dire than previously thought, and how the industry is responding, I'll turn it over now to our presenters who are sharing a slide deck. So Kent and Sharif, as soon as you'd like it, the floor is yours.
Hi, everyone. Kent Whitfield, as Tim said, I'm VP of Quality at Nextracker, and the subject of the webinar, as Tim so eloquently put, is understanding and mitigating the dangers posed by hail and wind. And really what I want to leave you with is an understanding that, where weather is involved, optimizing risk reduction for any one particular threat in a vacuum may not always be the best choice. We really need to think about the probabilities in this case of risk of hail occurring by itself, the risk of wind occurring by itself, and the conjunction, wind and hail together in order to do a proper risk analysis. Now, specific to hail and wind is that any active strategy for risk reduction really has to be fail-safe. Where thunderstorms are involved, power outage is certainly possible. So you really need to be considering, step one, do you have a battery backup system or something that, should the utility go away, you're still going to be able to, accomplish your risk avoidance. One of the things that we're going to be showing in a little bit, which I'm kind of personally excited about, is the fact that we do have some fresh data that just got in December of last year. Helping us to understand coincidence between wind and hail for what we would call significant hail, which is anything really over 2 inches in diameters, where we're starting to get into a range where we've got to think about how do we protect against it. The other kind of surprising thing that has come out of this research that Sharif and I have been doing is that we're seeing some evidence that when we get into larger format modules that maybe have cost optimized frames, that there may be a greater risk coming down the road for wind damage. Now, I think, at the end of the day, some environments are probably going to benefit from passive protection. And what we mean by that is that some products will have to be hardened against the specific climates they find themselves in, whether it's corrosion, high temperature, or in this case, potentially there's certain locations that economically make great sense for PV projects, but they might also represent an opportunity for significant hail strikes. So we're really talking about hail hardened modules. Now, it's part one is really, orientation on failure modes. Not surprisingly, the number one source of claims for large scale, especially large scale PV systems, is associated with weather. And this kind of makes sense when we think about a lot of the damage out there, whether it's, workmanship issues or electrical failures. These are going to be kind of piecemeal occurring at sort of the margins of the distribution. Weather can be very large scale in its impact. And, when we start talking about hail, certainly that can affect the entire site. And speaking of which, whenever we talk about hail, we're really operating from the ripple effects of this one particular event, which is the Midway Solar event that occurred in April of 2019 in Texas. Many of us have heard about the $70 to $80 million insurance claim this one event created, and really the subsequent hardening of the insurance industry against the threat of hail. And maybe even more importantly, the sensitization it's created in all of us, whether you're a project developer, a project owner, or independent engineers. What's unique about the threat of hail as compared to something like wind is that even though it's a very remote event for any one particular location, if it should happen, if all the distributions line up unfavorably, it can have an impact to the entire project site. Whereas, wind as a threat primarily tends to operate on the very outside exposed roads. So that's one significant difference. But at the end of the day, we really have to make sure that we're putting this into some form of perspective. There was a great seminal piece that came out about this time last year from G-Cubed, who's an insurer, called Hail or High Waters. I really recommended a reading for those of you that haven't already seen it. And it kind of helps us to gauge the Midway Solar event in some order of perspective. In this piece, they looked at the frequency of claims for which, hail is definitely on the board. It's larger than volcanoes, but it's approximately 3% of total claims. Now, this is compared to wind, okay? And this is the other threat that I want to talk about today. And that's about an order of magnitude larger, about 33% of frequency for this time period shown here. Now, that's the frequency piece of this, okay? The other part of it, which I think has captured most of our attention, is the total cumulative spend by threat. And there's where you start to see hail just, taking off, potentially surpassing that of wind, okay? What we are seeing on this graph really is this one event, Midway. And when we start to take that particular event out of the picture, just again for perspective, there's a little different picture that it emerges. And it's really putting hail basically on par with things like tornado, wildfire, snow, and ice storms. Okay. That's why, wind is somewhat out by itself, but I do want to point out that this chart would be showing us that maybe that particular threat is kind of starting to level. And what this could mean, because we don't see any evidence that windstorms themselves are going down, is that design practices are getting better. And that's fantastic. I mean, that's what we want to see. Okay, nevertheless, hail may be a very remote possibility, but should it occur, as we saw in the previous slide, it can be devastating. Now, in terms of the damage to PV modules, if we look about 12 months ago, there was a lot of things we just didn't know. And the reason we didn't know it is because as an industry, we've been testing modules since the early 1980s with one test. It subjects a PV module to 11 shots of a 1-inch ice ball traveling 52 miles an hour. Turns out no module fails. So we really didn't know where's the boundary between good and bad with regard to hail. And the fundamental questions that are shown on this slide were really important. You know, where's the impact energy difference between cells breaking in a bifacial module package versus a monofacial, between glass breakage in these two packages, and between front and back impact? Well, it's really thanks to the outstanding work of Sharif and the staff at RETC that we're beginning to understand the answers to these questions through all of the testing that they've done. So, Sharif, do you want to take over?
Kent,
Yeah.
actually, before we here, I had one question myself, and I apologize for interrupting you, Sharif. But you said that hail is a relatively kind of infrequent phenomenon that has had in the past these kind of large, noticeable results. I've heard it theorized that, you know, in a planet that is kind of being affected by global warming and is feeling these changes, that hail may become more frequent in that sense, and that's why it's, you know, becoming such a forward-looking, you know, we got to figure this out before it gets worse kind of phenomenon. Shouldn't that be taken into account when assessing the risk of hail damage?
Yeah, that's really a good question, because it's actually a source of a lot of debate right now amongst the preeminent researchers in weather. What we see from some of the most recent evidence is that the frequency of occurrence may not really be what's going on here. What we're really seeing is that it's most closely related to population growth. And the total cumulative spend by claims is most associated with the increasing cost of goods. So if there's a couple of pieces of research very specifically that I think address this really excellently. One is by Dr. John Allen and Tippett, that was published in 2015. And it really helps us understand that, you know, at the end of the day, there's not a strong signal for hail associated with increasing risk due to global warming. Now, that may not be true for all threats, okay? I think hurricanes specifically, there may be evidence that supports stronger storms, but we don't see it with hail.
All right, thank you very much. Appreciate that. Sharif, you may finally have the floor. My apologies again.
Thank you. No problem. No, that was a great question. Thank you. So as Kent mentioned, historically, certifying modules involved performing a hail test, which involved shooting 11 projectiles at a module. Each hail ball is, you know, measures 1 inch, right? We've never seen a failure there. So how do we go from that test to a test that actually can assess the risk associated with modules, where we can get a signal, a pass-fail signal from a module that says, this is a good module, or this is a module that can withstand a certain amount of hail impact in a certain region. So, and we needed to do that through a program that could produce repeatable and reproducible results. That was the key element. So we've worked over the past few years. We worked with industry experts such as Kent and others, and independent engineers, developers, manufacturers, to come up with a test program, a sequence that could assess the hail durability, the hail resistance of a PV module. And it's not necessarily to determine whether a module is good or bad, or whether it should enter the market or not. It's really to assess the resilience of particular modules with different bills of material, and how they would react to different impact sizes with different terminal velocities. The test really involves performing some initial tests on the module, characterizing it initially, going through some hail impacts, and then doing some additional sequential stresses to simulate the module being in the field long after it has gone through a hail strike, right? As Kent showed in many of his presentations, especially the Midway project that has gone through that hail storm, you can see a lot of modules. Obviously, that's a very unique project where a whole lot of modules were damaged. But there are so many cases where a hailstorm goes through a project. It impacts a whole bunch of modules, but not all modules get damaged. So you may have, let's say, an example, 10, 20% of the modules that are visually damaged with the glass actually broke. And the rest of the modules just are, visually, they look okay. So the first instinct could be potentially to go replace the modules that are broken and just continue operating the site. And that is not necessarily a great idea. We're finding out, and we've been talking about this over the last couple of years. And so we subject those modules that may not have necessarily shattered upon impact to additional stresses to understand the long-term reliability impact and effects on those modules. And what we look at, for instance, thermal cycling and how it helps propagate the microcracks that could develop upon impact into long-term severe cracks on the cells, and then assess, for instance, risks such as hotspots. And you can see one of the picture here is a hotspot failure, typical hotspot failure that we can see at the end of the hail durability test. So these are things that we had to put together to essentially assess from a systematic way how modules would behave and how we can systematically categorize them into bins, right? And so some modules, say, are going to do extremely well at high impacts and others may not. And what that would mean is, it would mean that as a developer, as a stakeholder, you need to assess the modules you plan on fielding in particular project sites, and just decide which module you want to put where. So a module that doesn't necessarily do very well with extreme hail risk could be perfectly fine here in Fremont, right? You don't have to worry about hail here, right? So that's basically what we tried to do. Good. So what did we find out over the past couple of years that we've been doing all this? So we've constructed a huge data set, hundreds of impacts, thousands of impacts, hundreds of modules, and what we found in general is there's a lot of variability, huge variability in the results, good and bad. And so what we tried to figure out is, okay, we have all this data set, it's great data, but how can we make sense of it? So what we looked at is the probability of failure. And so essentially, and this is something that, that's a trend that's actually going on in the industry, is not every module is going to break upon the first impact. And especially not every module is the same. And so different modules with different bill of materials are going to react differently under different types of impact. So what we looked at is, what is the probability of failure of particular modules with different bills of materials under different categories. And so what we looked at is we categorized these in three main buckets. Your first two big buckets are your standard run-of-the-mill modules that you're used to. And so the first one is your bifacial modules that we've been looking at for the past few years. And those are 2 millimeters by 2 millimeters, double glass construction, standard modules out there. That's basically, they dominate the market right now. The second is the 3.2 front glass with a polymeric backsheet. And those are the conventional monofacial modules that, have been kind of dominating the industry for the last 10, 15 years. So what we find and what we did is we looked at, okay, what is the probability of failure of the double glass construction with 2 millimeter by 2 millimeter glass? And we found that there is a 50% probability of glass breakage at around 57 joules. So that means, half of your modules could break with, in a storm that's going to, potentially impact them, that's going to cause hail balls to impact the module with 57 joules. That's roughly, in a lab setting, equivalent to about 1.5 inches, not 2 inches, not 3 inches, which is being reported in some cases, right? 90% of the modules would break at 97 joules. There is a wide variability in these, even at the P50 level. Modules start to fail at 45 mm, which is roughly about 20 joules. And, and some modules do much better, than others. Again, very bill of material specific, very construction specific, size specific. So there's a lot of, and these are, by the way, one thing to note here is these are heat strengthened modules. They tend not to be tempered. Now, the 3.2 millimeter bucket, and these are conventionally monofacial. Some bifacial modules use 3.2 millimeter front glass with a clear back sheet as well, and we've tested those. So you can see clearly here that 50%, there's a 50% probability of failure at 100 joules, almost twice as high as the 2 millimeter glass on glass. And that translates to roughly 2.5 inches, somewhere between 65 and 75 mm in diameter. Again, lab setting. These are not natural, ice balls. There's no way to control those. So all of these are very, very tightly controlled parameters to look at repeatability and reproducibility. Now, we did some testing on 4 millimeter front glass with polymeric back sheets. These are not readily available modules, so the data set is fairly small, and you could see that clearly with the wide distribution of the results, the wide variability, which is fine. That's just an indication that we didn't have enough samples. However, the overall trend, the prediction here is that 50% of the modules would break based on the data that we've collected at about 124 joules. And the P90 is around 180 joules. So you can see that there is a clear trend upwards as the glass thickness increases and the tempering process is more solid. Kent. So now here I just wanted to show something that's actually really interesting. So the point here is that this is 75 mm. On the right, the impact that you just saw is a 3.2 millimeter fully tempered glass, and you could see the shattering pattern. And on the left is a 2 millimeter by 2 millimeter heat strengthened glass construction, and you can see that the break pattern is very different than that of the 3.2 millimeter glass. The point here is that we wanted to point out really quickly is this is done at a steep angle, about 60-degree impact angle, 3-inch in diameter, and what essentially we found out is at a certain hail diameter, it really doesn't matter what you're going to do. So if the project is going to be in an area, in a zone, for instance, that is expected to have 3-inch hail, 4-inch hail, even larger, the modules are going to suffer damage, period. Now, there are some mitigation strategies you can employ to reduce the failure rate and save as many modules as possible. And then you need to assess what will eventually happen to those modules that do not break. But the point here is there is a point at where damage is going to be inevitable, right? You throw a hammer at a module, it's going to break. It doesn't matter what you're going to do. And but at lower impact energies, there are definitely things you can do. And one of the best things you can do is to assess the quality of the module and its resilience and resistance to different hail impacts at different locations, and then couple that with some mitigation strategies. Next, Kent.
Such as active risk reduction. Nice segue there, Sharif. This is really what started it all for us, which is, we've had an active platform in operation for over 2 years that we call NX Navigator. It was originally developed for plant owners and operators to be able to securely monitor and control their equipment for O&M, enhanced energy yield, and for safety functions, most notably in advance of a hurricane event, being able to put the entire site into a safety stow position. So it already incorporated site-wide controls for either local or remote activation. So it really wasn't a stretch for us to incorporate hail stow functionality. But step one is, if you're going to do that, you really should go through the necessary homework to demonstrate that it really is going to have a valuable risk reduction benefit to the user. And that's where we wanted to pull in an objective third party to be able to assess that benefit for us on behalf of the customer. And that's where we engaged RETC to validate that if you put a module into a position where the impact is non-normal, theoretically, of course, it's kind of an obvious statement. If the angle of impact is acute, there should be significant risk avoidance. But we wanted to still go through the process of generating the data to demonstrate that. Well, we did. That report was issued in March of 2020. We were actually one of the leaders on that. So we incorporated the hail stow functionality into the platform, and we gave the user choice over the direction of stowing. Now, for any active risk reduction, in order for it to really be effective and to be meaningful, there's got to be a few additional elements to it. It's got to be something that can be controlled anywhere securely. And the reason that this is super important for the category of hail is that what we're worried about primarily is synoptic hail. It's formed in thunderstorms. Thunderstorms, occur primarily in the afternoon, evening. So it could be at times when people are not at the plant. So you've got to be able to, when you receive the weather alert, you've got to react, and you've got to do it right away because there can be very little advance notification of an impending hailstorm. Secondly, it's got to be fail-safe because thunderstorms can be associated with power outages. It's kind of obvious. So, if you've got an active risk reduction strategy that doesn't work when there's no power, it's just you don't have a risk reduction strategy. So you've got to have that battery backup, which of course the Nextracker projects all have, products all have. And lastly, it's got to be fast. Again, you don't have much advance notice of these things happening. You may have at the outside 10 minutes. It could be less. So, this is something that we kind of pride ourselves in, is being able to get an entire site to go into a safety stow position measured in seconds. We can do about 60 degrees in 90 seconds. And so, this is why effective risk reduction has got to have additional aspects to it. So I mentioned that the user has choice over the stow direction, and this, really begs the question, and it's the heart of the challenge. What is the one true direction to stow? And it turns out there's always qualifiers to that. But a lot of time has been spent thinking about active stow strategies with respect to hail and wind. We know that wind with hail is relatively common. If you look at the body of Storm Prediction Center's severe weather database information, it would suggest that about 18% of the time you do have severe wind with severe hail. In order to answer this question, the approach that was taken here was to look at the myriad of automated weather systems installed throughout the continental United States and identify a weather station that was within 10 kilometers or less of an actual hail strike. These weather stations give us high precision, high resolution wind gust speeds. So we found one that's in close proximity to an actual hail strike within the same time frame as the hail strike. Now, based on some earlier work that was done by Lombardo and Zicker in 2019, they identified regions of similarity, and these are shown here in this colorful US map. And the one that we really want to focus on is what they refer to as the Southern Plains region. This is the Texas-Oklahoma region. Where it happens to be, you're going to find some of the most severe hail and the most severe winds. So this is the region to focus on. So an analysis was done by Dr. John Allen of Allen Weather Risk just in December of this last year. Basically took this information and produced this box and whisker chart that we see on the right-hand side. And what we can see in there is basically across the board, regardless of the bin size of the hail, which is shown on the horizontal axis there, you can see that the median wind speed represented by this red line is about 12 to 18 miles an hour, okay? So this is wind co-occurring with hail. And we're seeing it based on hail size, and we're seeing the actual gust velocity in the vertical. Now at the very top here, maybe a little tough to read, but it's the number of records that are associated with the statistics there. This also gives us an idea of frequency of each one of these bins. Now, what we consider to be significant is anything over 2 inches, and this is based on the data that Sharif was just sharing with us. Okay, so the median's 12 to 18. Let's talk about the extreme. When we get up to the 99th percentile in wind speed, we're talking about winds that are around 50 miles per hour, maybe a little bit less. But that's really good information because it gives us an answer that we can use then to start to address which direction to stow in. So what we're seeing on this slide here are 2 kinetic impact energy charts. Yes.
Before you move on, do you mind if I have another quick question?
Absolutely.
Kind of slide there. Yeah, so the median wind speeds you showed for Texas and Oklahoma seem to be like significantly lower than I've heard others talking about when they speak of hail with wind. Is this being underestimated, and could that make the risk of hail damage more likely, or those median speeds seemed a little bit low to me? So if you kind of extrapolate on that a little bit more.
Yeah, sure. Yeah, and this is really an important point because some people may not be aware that what we find in the severe weather database are records that are associated with observations by people. Okay, it's not data from calibrated instruments. It is basically observational records. And about 29% of these records are from people that have been trained to know what they're seeing, okay? And the second most is just sort of the general public. And if you go to the NOAA National Weather Service site and actually look at what this record involves, it just says, what was the size of hail? And if you think it's severe wind, how fast was the wind? And they pretty much don't even track wind until it's about 50 knots or more, which is 58 miles an hour. And that's why you'll see that this data tends to skew towards much larger numbers. And it's really just based on people's impressions of, was a tree uprooted, was a branch broken? And that's why it is different. And this is why it was so important for us to use these automated surface observation systems, or ASOS weather stations, because they do provide us with calibrated high resolution wind speed information that we can use to really get a better handle, we believe, on hail with wind.
Awesome. Thank you.
Yeah. And I'm sorry, I'm just trying to move along here quickly. So anyways, the kinetic energy impact charts are shown on this slide. Okay, so on the left-hand side, we've got into the module facing into the wind at 50 degrees. On the right-hand side, we've got it facing away from the wind at 50 degrees. Now, the horizontal axis is an ice ball diameter. We could think about that as a very conservative, naturally forming hailstone diameter. In the vertical axis, we've got wind speed. The colors that were chosen for this chart are based on the data that Sharif showed us for the P50 results. If the color is green, there's very little probability of module damage. If it's yellow, we're seeing an increasing likelihood from cell to actual glass breakage in a bifacial module package consisting of 2 millimeter by 2 millimeter heat strengthened glass. As we go into the red, we're talking about the increasing likelihood of monofacial module damage. And by that, I'm really saying 3.32 fully tempered glass with a flexible backsheet. Now, let's superimpose the wind speeds that we showed earlier. At the median wind speed, what's the difference between the different stow directions? It amounts to about a 1/4 inch size. Now, given the uncertainties that are involved here, we cannot consider that to be a significant difference. Okay, really means that the stow direction is not material at the more at the 50% wind speed probabilities. What if it is, significant hail that is co-occurring with the 99th percentile? Okay, there we're starting to see a difference. It's about a 3/4 of an inch difference in favor of the backstow position. But here, we also have to note we're at a moderate wind speed. And so now we've got to be asking the question, did the tracker manufacturer take into account aeroelastic effects that will protect against any sort of a dynamic failure mode? And this really gets us into, okay, what is the risk of damage due to wind just by itself? So NIST studied non-hurricane, non-tornadic wind speed return intervals spanning from 10-year return interval, all the way to, I kid you not, 100,000 years. And what's striking about their analysis, and this is based again on, this is based also on ASO's weather station information, is that the likelihood of damaging winds across the U.S. is much more ubiquitous than hail is. Even in short return intervals, such as what's shown on this slide, 10 years, that's a 10% probability per year of winds that are in excess of 50 miles an hour. Now, this is important for trackers, okay? Because what we have found, Nextracker has installed a cumulative amount of trackers worldwide of about 50 gigawatts. And we find ourselves in all countries, and we often find ourselves co-located with other systems. And what we found in certain moderate wind speeds is that there are dynamic failure modes that can actually cause a destruction of the tracker. These, you may have heard of terms like torsional flutter, torsional galloping, torsional divergence. They're all describing the same thing. It's basically a resonant failure mode that's being brought about by vortex shedding. And this creates this positive feedback scenario that ultimately leads to destruction. And it's something that's unique to flexible structures. So if the tracker manufacturer hasn't done an adequate job of doing an aeroelastic impact study for their product, which is not necessarily part of the code approval procedure, then it can suffer these dynamic instabilities in as low as 40 mile per hour wind speeds. So this is why, wind risk has to be taken pretty seriously. And I think there's an emerging issue that we're seeing on some of the larger format modules that may be another threat to consider. Right? Sharif?
So essentially what Kit just said in his last slide is that wind is everywhere. Hail may be restricted to certain regions based on its severity and its potential impact, but wind is a real problem. Now, one thing to note is over the past few short years, everybody has noticed that the modules are getting larger, and they continue to get bigger, right? As the modules get larger, the way I usually explain it is they're like sails on a boat. So the larger the sail, the larger it's going to resist wind, right? And also the more area to collect snow. And so one of the things that we do all the time is we perform qualification on modules, both for certification and for engineering, for sites. We look at the module's resilience to snow and wind. And some of the things that we've been noticing, some of the negative trends that we've noticed, is that the modules are becoming less resistant and less able to withstand the snow and wind pressures that they're going to be facing in the field. And this is due to a variety of reasons. As you can imagine, if a module is going to be increasing in area, by 20% potentially, or even more, it's going to get very heavy. So it's natural for the manufacturers, and by probably strong requests from the EPCs because of their weight, they needed to reduce the weight of the module. And so that's how the thin glass came about, is really to make them easier to handle and to install. And then of course another drive is the cost, right? And so one of the things that the cost has been driving is also the optimization of the frames. So the frames are getting thinner in cross section, they're getting smaller, and they also had to reduce the lip in the back of the module, which provided quite a bit of structural integrity, in order to allow for the light to actually make it to the perimeter cells. Otherwise, the frame caused shading to the cells, and it reduced the efficacy of the bifacial technology, the bifacial cells. So what we're finding out is when we subject these modules, these larger modules, to their intended loads in these particular high wind applications, is they're breaking. They're breaking in very systematic ways. And what we've been able to confirm from our engagement with a variety of different developers and many inspections that we performed in the field is that these modules are breaking in similar ways in the field. So this is not an artifact that we're seeing in the lab, but this is something that actually is happening in the field, and potentially will continue to happen. Of course, depending on the application and the stow strategy, and what the O&M team is going to do with the tracker facing a strong wind. And this is something that we're trying to bring up to everybody's attention. But yeah, so Kent.
Yeah. Thanks, Sharif. So at the end of the day, just to kind of wrap this thing up, there are some recommendations that I'm hoping people will take away from this presentation. In high wind scenarios, there's benefit from being backwinded. Just have to be positive that the structure is rated for it. System should never transition through zero during high wind speeds just to avoid dynamic failures. This is something we've automatically programmed into our products to take a protective wind stow when the wind speed's high to avoid this transitional phenomena. And the speed of transition, again, when you get the alert that there may be an impending hailstorm, you don't have much time to react. So it's got to travel fast. And active protection has to have a fail-safe. It's got to be protected against single point failures, or it's just not an effective strategy. The last information from my part of it is think about the median wind speeds here. It basically says that the stow direction is somewhat immaterial, but at the end of the day, Nextracker provides a platform that gives you choice as to what you think is best for your particular situation. Sharif?
And I think one of the key takeaways from my side here is developers or stakeholders in general need to understand what module they're purchasing and installing and where and why. And so modules can easily be assessed for their hail tolerance, and this needs to be performed on a bill of material basis. And that's based on the variability and results that we've been seeing over the last few years. Not every module is made the same way. Not every glass manufacturer manufactures glass the same way. Not every process yields the same stresses or is able to minimize the stresses imposed on the modules, which could make them less resistant to hail. Modules are getting larger. These are the technology is increasing. It's all great. This is all great. The cost is going down. So all of these developments are great. However, there has to be an active and concerted effort to understand the risks associated with whatever module is being selected. And so make sure your module is hail hardened if you plan on installing it in a region that's going to be subjecting those modules to frequent hail events with high severity. The next thing is to understand where you're installing these. So if you assess a variety of different modules and you find out that some of them are or are going to resist are going to be resilient for a particular region and regions and others are not, you need to be able to couple those modules with the right location. And how do you do that? Well, there are tools. Our friends at VDE, for instance, America, have developed a variety of weather risk tools. There is a return interval of hail by size and frequency, and this is a product that you can essentially provide them with an actual location by GPS coordinates, and they tell you, what is the return interval for hail, by size and frequency for that particular location. There's the co-probability of hail and wind, and this is really, really critical, and this is what Kent's been talking about. This helps you understand and make informed decisions on how to stow, in which direction, when to stow, as well as other financial loss models, such as the average annual loss and the probability maximum loss. And these are, taking all the mitigation strategies that you're putting in place, both in terms of active tracking and stowing, to the modules that you're selecting and the data that's being generated, and then you can have an assessment and a predictable assessment of what the losses could be in the event of hailstorms based on the return interval that's been calculated. And so once you devise all of these, and by the way, for those tools, feel free to reach out to John Sedgwick, president of VDE Americas, who can do a much better job at explaining those tools. But I think they're really, really important in assessing the site risks, for projects that are being planned. So, devise a mitigation strategy, pick the right module, and at least you have done the best you can to ensure the lowest possible risk associated with weather, severe weather storms and hails.
Keeping in mind those active stow requirements, speed, backup, etc.
Certainly. And thank you guys for that wonderful presentation. So with our last 12, we can go a little bit longer minutes here. I want to get into the Q&A if both you, Sharif and Kent, are ready.
Absolutely.
Yes, sir.
Cool. First question here kind of goes into stow strategy and overall kind of how hail acts as an element of weather. And they're asking, hail can fall on the PV system and kind of make contact from different angles. How does the system react when the hail pattern or direction changes? And have these kind of direction changes ever been seen maybe mid-storm, mid-event?
Wow. Okay.
Softball to start it out here.
Yeah. I'm thinking through this. So what I have seen, and it was really kind of validating, was saw some videos of hail striking a PV system, and again, it was Texas. And what you saw was that there's a lot of variability in hail. We think about it as being a one size kind of event. It absolutely is not. And what you see is that if it's co-occurring with wind, you'll actually see it coming in at different angles. The smaller stuff is much more entrained by the horizontal wind speed. As it gets more vertical, or as it gets larger, it becomes more and more vertical. So even within one storm that's going in one prevalent direction, we see a range of vectors of this thing. Now, the stuff that's coming in much more horizontally just doesn't have that much energy. Stuff coming in more vertically, that's the stuff you want to be protecting against, and that's why the stow angle can be an effective risk avoidance. Mm-hmm. I hope that kind of covers that.
Yeah, I think it did. Sharif, this next question is specifically for you, and they were asking if the RETC HDD test is useful for predicting module hail resistance, or do you think that modules perform better under this that perform better under this test could be more robust in the face of other kind of environmental stresses as well. So basically, if something performs well in your tests, does that mean it will perform well in the face of other extreme weather phenomenon?
Yeah, it depends on the weather phenomenon. So the hail durability is specifically designed to assess the module's impact ballistic resistance, right? Hail impact resistance. So essentially, what we're doing is we're taking modules, we're impacting them with various hail ice balls to simulate hail impact, and then we try to understand and assess what is the immediate impact on the module. Does the glass shatter or not? And if it shatters, that's it. That's the end of the road for that particular bill of material. And if it doesn't, what will happen to the module in general? That does not replace per se all the other environmental effects. For instance, the hail is very localized. It's an ice ball that hits the module in a specific location. That will not, for instance, replace understanding the wind resistance of that module under high winds, right? In different stow or different positions, not so much stow positions. It could be a fixed tilt, it could be anything, right? So, and then it certainly doesn't assess the module's wind or snow resistance based on the mounting location, whether it's mounted via bolts, rails, clamps, whatever that is, right? That will also not replace the module's humidity resistance. So if it's installed in a high humidity region like Florida, like Hawaii, there's going to be other issues that you have to worry about, right? Thermal cycling, whether the module is, and vibration. I mean, so the overall threshold test that we provide at RETC, which is a bankability due diligence, technical bankability due diligence, looks at everything. It's a collection of tests where we're looking at how the module is going to perform in general. And when you get a positive report on that, it's all the check marks. I mean, we publish the PV module index every year, which essentially requires manufacturers or products to pass everything. It's not just you do well on one test on hail and then you get a great review and therefore you can install it anywhere. No, there are definitely other tests that I think are very critical and essential in ensuring the module is going to last for 25 or 30 or 35 years in the field, beyond just the hail. And I'd be more than happy to discuss this, offline with anyone who would like to explain all the other tests that are equally important.
I want to jump in on one little thing though, because please. I don't know if you remember, Sharif, there was this one module that we tested where it was hit in one location and the shell and the cells in the entire module shattered. Okay. So, there are situations where you might be able to use this one test to uncover some substantial weaknesses in a product. Okay. You can't use it as a proxy for all different environmental exposures, like Sharif was saying, but it may help you to uncover a weakness to be very concerned about.
An interesting question here when we go to the topic of testing, and this is going to lead us down a rabbit hole that could be its own webinar. So I will try to pull us out of that rabbit hole. But the question here, and it's going to start with Sharif, and then it will build, is, regarding your impact testing, it seems that you only do it on the glass on the front of the module. Has any impact testing been done on the back sheet to test resilience of the back sheet? And then here's the part that'll get us down the rabbit hole. Would it ever be optimal to stow with the back sheet facing hail as opposed to the front of the module? And if not, why not? Or if so, why so?
Yeah, so we've actually performed that testing. We've done quite a bit of backsheet impact. So there are two things to keep in mind here. So there are two types of modules. There's the double glass modules and there's the glass polymeric backsheet modules. So when you're looking at the glass modules, you have the same glass in front and the back, right? Mm-hmm. And so essentially the benefit of impacting the module on the back is not substantially higher because you're still impacting, glass with the same thickness. And in so many cases, when we do our construction evaluations, manufacturers use the same glass in front and back. You can just imagine it's much cheaper to stock one bill of material, one type of glass, as opposed to stocking, different glass for front and back. And yeah, so from that perspective, I don't think there's a huge benefit. But when you look at modules that are designed, for instance, with 3.2 millimeter glass, which is thicker, it's actually fully tempered, and it resists front impact. So the whole point of actually using, if going to that direction, well, not the whole point, but one of the benefits of going in that direction is that the front glass is going to survive a direct impact better than a 2 millimeter glass. And from that perspective, positioning the module in such a way that you're subjecting the back of it to a hail strike kind of defeats the 3.2 millimeter front glass. So that said, as you would probably think intuitively, the difference between impacting a cell, a very brittle 200 micron or 180 micron or 160 micron cell, with a projectile, and protecting that cell either by a 3.2 millimeter glass or by a few microns, potentially 1 millimeter of a flexible polymeric backsheet, there's a big difference. I mean, obviously, it's going to cause the cell to break if you hit it from the back. That's basically the short story. Now, there are some caveats to that statement, and that is, if you're going to do that, the idea is that you would subject the back of the module to hail impact only under specific conditions. And I'm saying this to cover, for instance, something that Peter Bostock has been talking about, one of the industry experts out there. So essentially, his point is, well, you could and should do that when you know that the hail impact from the backside is only going to come from very small projectiles that are going to be pushed by small wind speeds. Otherwise, the large projectiles are going to tend to fall more or less vertically, because they're gonna have a much bigger mass, and they're going to require a much higher speed to move, right? All I can say is, yes, that I tend to agree with those assumptions. You just have to really, really understand wind characteristics very, very well, especially co-probability of wind and hail, and maybe more critically, changes in wind patterns mid-storm. Because if you make an assumption that, okay, I'm going to only get today, because of this hailstorm, we're only going to get, say, wind speeds of 20 miles per hour. If mid-wind storm you get a gust of 60 miles per hour, 70 miles per hour, I think Kent is going to probably attest to that is probably not a good position to be in, with the back of the track or the back of the module to the wind, because it's going to put some fairly substantial pressure on the module on the negative side, which the module and potentially the tracker may not be designed to sustain.
Well, it's definitely, it's one of those questions that you have to ask. Did the tracker manufacturer do their homework and anticipate this as a risk factor? One thing, if I could just go back just very briefly,
it would appear that we have lost Kent briefly. So we are getting close on time here at the end of the webinar. So if we don't get Kent back in a few seconds here, I'll just wrap this up. My apologies for this kind of weird wrap up to it. But yeah, thank you for attending today's webinar, and thank you once again to our wonderful presenters who hopefully didn't get struck by a meteorite or something. We should be seeing in a couple of seconds here a screen for some of our upcoming print publication articles, or some of the articles that we are featuring in the print publication. If you cannot see them now, both are authored by our wonderful editor, Ryan Kennedy, for the PV Magazine USA site, and we are also contributing monthly to the PV Magazine, there it is, print publication. and you can get a 10% off code, a subscription to PV Magazine USA with the code webinars10. That's our special treat to you for attending this webinar, although the treat should be the knowledge you glean. So maybe 2 treats. But yep, right there you can see both of our articles by Ryan Kennedy. And on the next slide here, we should have some upcoming webinars coming up. That should be coming up on your screen any second now. Yep, there we go. Suitable solar and storage, new residential solutions from Jinko Solar. That is coming up on February 9th, the day after my birthday. And then on February 10th, we have reducing the environmental impact of PV mounting structures. There's a QR code in the corner there if you'd like to get more information on our upcoming webinars or revisit a webinar such as this. Or you can go to www.pvmagazine.com/webinars. And I believe that will do it for us today. So one more time, thank you to our excellent presenters.
Tim, our speakers are back if you want to resume. I think we had a slight internet issue there.
Okay. Yeah. I mean, I can open this up for final comments here, guys, before we hop off.
So apologies for whatever happened there.
All good.
Thanks everybody for attending. Just what I was trying to get at is that, hail does come in a number of different angles, some of which may be hitting the back sheet, especially if you're in a backwinded scenario. Have looked at this with those kinetic energy impact charts that I showed earlier. You got to be at a pretty darn high wind speed to be at risk of cell damage from a backsheet impact. But it can happen. So that was the answer.
Appreciate it. And yeah, sorry for the interruption there, but thank you for the insight. Sharif, any final thoughts?
Yeah, thank you, Ken. Thank you, Tim. I think essentially the key takeaway is do your testing, select a program that is systematic and that looks at variability in the results in a very systematic way, and do your homework when it comes to your mounting structures. Make sure that the structures are designed for the environment that you're installing them in, as well as the modules that you're installing on top of them. So just because a structure is great for a particular module, you increase the module by 20%, it needs to accommodate that. And it also needs to accommodate the severe hail risks where the project is installed. There are tools out there, tests that can be performed on the modules, the trackers, and there are technical tools that can help you assess the risks associated with the installation location.
Yeah, as an industry, I think we're ultimately going to be looking for products that are differentiated by risk for different kinds of situations. And we're going to require a combination of both active risk avoidance and passive risk avoidance in order to really capture the attention of the insurers and to lower the overall risk for the owner. So like I said, with the active stuff, it's super important that there are additional characteristics that make sure that active risk avoidance is going to be effective always when counted upon.
Mm-hmm. Great. Well, thank you for that last little tidbit. That's something I've always been interested in, is whether or not a market would develop specifically for certain types of geographically or kind of climate related instances. So it's cool to get that perspective that, this is something that we expect to be established. So once again, thank you to our presenters and thank you to our audience for joining us here. I kind of already did my wrap-up spiel back before. I didn't know if we were going to get Kent and Sharif back with us. So have an excellent day. And please, you will receive a survey after the end of this webinar. If you could please fill that out and give your honest feedback. It helps us to develop webinars better suited for you, the audience. And that is always the goal, to maximize your interest in our presentations and webinars here. So once again, I'm Tim Sylvia. I'm an editor with PV Magazine USA, and thank you very much for tuning in.
Thank you.
Yep. Cheers.